Next, we will talk about this coupon collectors problem. So let's see what it means. Okay, so a long time ago in Taiwan, there was some lucky draw function held by this family mart. So if we purchase enough number of items, okay, so if we pay enough, okay, to buy enough things at family mart, we can have a chance to do a lucky draw. And with one lucky draw, we can obtain one of the figure of these 10 deities. Okay, so there are 10 different deities, and then each one of them will have a little figure that we can get. And then let's say the chance of getting each of these deities is equal. So we have equal probability to get any one of them. And suppose that you are a fan of these deities. You want to make a full collection. So we want to find out what is the expected number of draws to get a full collection of all the deities. Notice that the first time we may draw a certain deity, and the second time it is all random again. So we may be drawing the same deity again and again. So in the worst case, the number of draws to get a full deity, to get a full collection, will be infinite. So it could go up to infinite. But if we are very lucky, then we just need 10 draws to get all these 10. So we want to find out what is the expected number of draws that we need. And in general, so we can say that there are n different cards that we have, and then with each draw we will get a random card, and the same card may be drawn again and again. So this is like sampling with replacement. So we are going to draw some card and put it back, replace it back before the next draw. And here we define x to be the number of cards drawn to get a full collection, and then the target here is to find what is the expected number of x. Now this problem looks rather hard from the beginning, but in fact it is very simple if we are lucky enough to see the key point. So the key point here is we are going to break the process of the whole lucky draw process into n stages. So the first stage, we focus on getting the first card. Okay, that's easy. So we draw a card and then we will get the first card. And in stage 2, the second stage, our target is to obtain a card that we have not seen before. So our target is to make the collection to have 2 distinct cards. So draw until we get a distinct card. And similarly, stage 3 is after stage 2. So we again, the target is to obtain a new card that we have not seen before. So in stage 3, the target is to make the full collection to, not the full collection, the current collection to contain 3 distinct cards. So we end at stage 2 and then begin stage 3, and after stage 3, then we will have 3 distinct cards. So in general, after stage K, we will have K different cards. Okay, now the purpose of breaking the process is going to be obvious in the next page. Okay, suppose that we let xk to be the number of cards drawn at stage K. Then we will see that x of k is actually a geometric random variable. It is like flipping a coin. So in the first stage, any card will be okay. But in the next stage, only n-1 out of n cards will be okay. So we are going to, for stage 2, we are going to flip the coin until we get a card. The success probability of each flip is n-1 divided by n. And in general, for xk, it will be the geometric random variable of n-k plus 1 divided by n. Okay? And after defining this x of k, then everything will suddenly become very easy, because the total number of cards that we need to draw is the number of cards that we draw in stage 1 plus the number of cards that we draw in stage 2, and so on and so forth, up to the number of cards that we draw in stage n. So x is equal to the summation of x1, x2 up to xn So by linearity of expectation, expected of x will be expected of x1 plus expected of x2 plus expected of x3 up to expected of xn. And now, because we know the exact behavior of each xk, so we can find out what is the expected value of each term. So the first one is n over n, the next one is n divided by n minus 1, and so on and so forth. And the last one is n divided by 1. So what does that mean? So it is like n times 1 over n times 1 over n minus 1, up to n times 1 over 1. And then what is it? It is exactly the same as n times h of n. Okay, so this is the end of the analysis of the coupon collectors problem.